This is the Calculus 1 lecture for section 4.7, which is about finding the area between curves by using the definite integral. So when I first introduced the definite integral, I described it as the area under a curve, or as representing the area under a curve. So like if you have a curve, my iPad's acting up, I'll pause and draw the curve. So if you have this curve, y equals f of x, the shaded region, the region that's shaded in purple right there, is represented by this definite integral. So I can say area of the shaded region. Oh, you know what? Let me turn off my video. I want to make sure I'm not covering anything up. So the area of that shaded region can be represented by the definite integral from a to b of f of x dx. So this section is really just a continuation of this idea. It's the same exact idea. It just shows us that we can also use the definite integral to find the area between two curves. So we can find the area under a curve, and we can also find the area between two curves. So I'll draw another graph, but this time with two curves. So here's just another graph with two curves. So we have y equals f of x on top, y equals g of x on the bottom. And then the region that I shaded this time is like a region between those two curves. And so using the idea of the definite integral being the area underneath a curve, we can say that the area of the shaded region, when we have like that our shaded region is between two curves, we can also say that this can be represented by a definite integral, because we know that the definite integral from a to b of just f of x dx, I'm not going to quite write the f of x just yet. I'm sorry, I'm not going to quite write the dx just yet. I'll write it in a moment. But we know that the definite integral of f of x from a to b, we know that that area includes this part that I'm shading in blue right now, right? But if we want only the area that I shaded in purple, we need to get rid of the blue, like I'm getting rid of it right now. And the way we get rid of it is to subtract the area under g of x, because the area under g of x was the part that I was shading in blue, right? And so I don't want that. I don't want that area. I just want the area that's between f of x and g of x. And this is our little like guideline for finding, now I'll put the dx. This is our guideline for finding the area between two curves. You'll set it up as a definite integral, and just make sure you have the, I'm just gonna box this here. Just make sure that you put the curve that's on top, like make sure that goes first in your definite integral, because it's always gonna be the top curve minus the bottom curve. So the f of x, that's your top curve. And then the g of x is your bottom curve. So it's more practicing integration and practicing using fundamental theorem of calculus and practicing recognizing the definite integral as an area. So let's jump into homework. let's look at the first problem. So it says set up the definite integral required to find the area of the region between the graph of y equals 18 minus x squared and y equals negative 3x minus 10. And so I'm going to enter those two functions in Desmos. So we have 18 minus x squared. I'm going to write y equals 18 minus x squared. And y equals, what was the other function? Negative 3x minus 10. So I recommend using Desmos just so you can get a quick picture. Like, don't, yeah, you can get a quick picture. And since we're trying to find the area of the region between these two functions or between these two graphs, let's see where these two graphs meet up. So, so notice like they're asking us to find here. I'm gonna like shade in the region that's between these two graphs. I'm just gonna shade that in. What color shall I use to shade? I think I was using purple, right, in my notes. So let's go ahead and use purple. So I'm just gonna, I just want you to see the area that we're trying to find. It's this area here that I'm shading. So that's the area of the region between these two curves. So it's all of this, all of this, all of this. And so when I set up my definite, in order to set up my definite integral, what I'm going to do is, first of all, like figure out where this region begins and where it ends. Because with my definite integral, I have to have like, I have to have a top number and a bottom number, right? Like for the limits of integration. So here's my elongated S for my integral. And at the bottom, I'll have the place where my shaded region begins. And at the top of this symbol, I'll have the number where my shaded region ends. So I love Desmos for this because I can just, like if I didn't have Desmos, I would have to take these functions and set them equal to each other and solve for x, which I can totally do, right? But look, I can also go on Desmos and look, I have the place where my shaded area begins, that's at the -4. And down here, I have a place where it ends, that's at the 7. So, so if I were to take 18 minus x squared, set that equal to -3x minus 10, it looks like I would get -4 and 7. So, which, yeah, it sounds like it wouldn't take a long time to get that, but using Desmos, I get it right away. And we're not practicing solving quadratic equations right now. So feel free to use Desmos to get these numbers. So the -4, that's where it starts. That's what's going to go on the bottom. And then the 7, that's where it ends. That's going to go on top. Here, the x values in those ordered pairs. And then from there, what you want to put after this is you want to put the top curve first and then minus the bottom curve. So it's always, when you set these up, you'll always have top curve minus bottom curve. So always top curve minus bottom curve. So looking at the graph again, notice that the parabola is on top. And the parabola is what matches, I mean, that's the quadratic function, right? So this one, 18 minus x squared, that's on top. This is the top curve. And then -3x minus 10, that's the bottom curve. So top curve minus bottom curve, use Desmos to determine where you're, determine these numbers, the limits of integration, the -4 and the 7, like where the region begins and where it ends. And you can also use Desmos to determine what your top curve is, like just quick picture. You can see what curve's on top, which one's on the bottom. And then setting up your definite integral is pretty fast after that. So we'll have our top curve, which is 18 minus x squared. You know what? I'm gonna put a bracket here just to, or you can put another parentheses. So we have 18 minus x squared, that's a square. And then we'll have minus our bottom curve, so minus the -3x minus 10. Close our bracket and then dx, and that's going to be our answer. Now, of course, you can simplify this if you want. If you don't want to, it's fine if you don't. If you do go ahead and like actually find the area between the two curves, then I would definitely simplify this. But I think for this problem, they're just asking us to set it up. And I think it's helpful, again, like in situations like this, you know, like where you're learning this technique and or learning this process, I think it's helpful to not simplify, you know, like when you're like the goal is to make sure that you know how to set it up. So I would actually recommend not simplifying just yet. And then later on in this section, then then you will have to simplify. But like while you're like just learning this process of setting up, I really like the idea for just for your brain to like focus on this, the setup. And then afterwards you can do the simplifying. So there we go. Let's look at another one. Which one? Oops, I didn't mean to stop the share. Where's my beautiful dog, Maggie? Let's look at number 3. So number 3, it says set up the definite integral required to find the area between the graph of y equals 12 minus x squared. That's y equals 12 minus x squared and y equals 18x plus 89. And this time, notice, look at it. They actually give us, this time they actually give us an interval. So it says over the interval -4 to 1. So because of that, right away, I can put here -4 at the bottom and 1 on top. And now I'm going to go over to my Desmos where I have the functions graphed. And let's look at what's happening between -4 and 1. So again, notice this time they gave us an interval. They said -4 to 1. Excuse me. So because of that, when I go to Desmos, that's what I'm gonna like really focus on that interval, the interval from -4 to 1. And oops, I'm noticing that -4 is like right here, right? And then 1 is right here. I'm just gonna label these. Okay, now we can see clearly. So here's -4, here's 1. So we're basically, I guess 18 times 1 plus 89. That's really high up. But I don't really care. What I know is that I'm finding the definite integral from -4 to 1. And all I care about is what functions on top, what functions on the bottom. And I'm noticing that this time it's the line that looks like it's on top. So, and the parabola that's on the bottom. On this interval from -4 to 1, the line is on top. So this is the top function, and the parabola, the quadratic function, that's the one on the bottom this time. So, and again, like be very careful to like pay attention to your intervals. So in this case, it was -4 to 1. So between -4, which is right here, and 1, which is right here, the blue function, that's the line, that is on top, right? But like if they were asking you for the area between some other interval, notice there's a point where the parabola is on top, like over here, you can barely see it, but look right here, parabola is on top. So pay close attention to your interval that you're given. Okay, so I'm going to set up the definite integral. So we'll have the definite integral from -4 to 1. And then again, my top function goes first. So I will start off with my top function, which is 18x plus 89, minus my bottom function, which is 12 minus x squared. And I end it with a dx, and I need to put my square. That's my square. I hope you can read that. But if you can't, I'm about to type it in the answer. There, that looks better, right? Okay, so I'm about to type this in the answer. So let's see. So again, top function was, 18x plus 89. Bottom function was 12 minus x squared. And there we are. Let's look at another one. Number 5 seems to have a lot going on. Let's look at this one. So this one, number 5, says find the area between the curves y equals -0.3x and y equals 2.4x plus 1 from x equals 0 to x equals 5. So what was the first function? Y equals e raised to the power of -0.3x. -0.3. Okay, yeah. And then the next one was y equals 2.4x plus 1. And then the next, and then it said from x equals 0 to x equals 5. So this time they're not asking us to just set it up. So this time we actually have to find the, we'll have to do the integrating. So it looks like numbers 1 through 4 are just set up. And then number 5, integrate. So it says from x equals 0 to x equals 5. So they're basically giving us our interval right there. I'm going to go ahead and graph those. X equals 0, x equals 5. So we have the vertical lines there. And let's look at the picture that we have. Okay, so x equals 0, that's the green vertical line. X equals 5, that's the purple vertical line. And then it looks like the area that we're trying to find, the area enclosed by that region, is right in here. This right in here. And I'm noticing that this area that I'm shading, so that's the area enclosed by the region created by these equations right here. And the area that I'm just shading, I'm noticing that we have the line on top. So I get to say, I'm going to set up my definite integral, right? We'll set up my definite integral. So I'm going to have the definite integral from, and these numbers were given to us in the beginning. So we know we're going from 0 to 5. So from 0 to 5. And then I want to say, okay, what function is on top? The line is on top, right? The y equals 2.4x plus 1. So it looks like this is my top curve. And then e to the negative 0.3x, that one's on the bottom. That's the red curve you see on the bottom. So when I set this up, I will start off with my top, 2.4x plus 1 minus my bottom, e raised to the power of negative 0.3x. And I'm going to go ahead and write this on my iPad because now we have to integrate this. Now we have to evaluate this, find the definite integral. We get to practice using the fundamental theorem of calculus again. So that's good. So yeah, I'll go ahead and write this and then we'll actually find the definite integral. All right, so we're going to use the fundamental theorem of calculus to find this value right here, which means we first have to integrate the function that we see inside. So that 2.4x plus 1 minus e to the negative 0.3x. So that's our first job, is to integrate this. The 2.4x, I recognize that this x is being raised to the first power. So using my kind of power rule for integration, I'll have x to the 1 plus 1, which is 2. Well, I'll actually write it out over 1 plus 1. So I just used this rule that the antiderivative of x to the n dx is x to the n plus 1 over n plus 1 plus c. I just use that rule. And then next, which is really the same rule, but not as obviously the same rule, that derivative of the antiderivative of 1 is just 1x. And that's because we know the derivative of anything times x is just that thing. So if you have a constant, just stick an x next to it when you're integrating and you're good. And then last of all, the e one is a little bit tricky because, so we know that the derivative of e to the x is e to the x. But in this case, we have e to the g of x. So we know the derivative of e to the x is just e to the x, right? But in this case, we have e to the g of x. And the derivative of that is e to the g of x, but then we have to multiply that by g prime of x. So if I put as my antiderivative for e to the negative 0.3x, if I just put e to the negative 0.3x, I know its derivative. Like if I were to like check this and find its derivative, I'd have the derivative of e to the negative 0.3x is e to the negative 0.3x, but then times the negative 0.3, because that's the chain rule. That's the derivative of the g of x, which in this case is negative 0.3x. So in order to compensate for that negative 0.3, and like in order to not have it, I'm going to divide this by negative 0.3. And that way, when I do differentiate this, like if I divided this by negative 0.3 in the beginning, notice the negative 0.3s will cancel each other out. So, okay, so I'm gonna get rid of this and keep going. And that's also the reasoning behind, like behind the first rule that I wrote in the corner. Like the reason we divide by the n+1 is because in the power rule, that n+1 comes down to the front. So it's like compensating for that. From here, I put my limits of integration, the 0 and the 5, and I'm going to apply the fundamental theorem of calculus, but first let me just rewrite this as 2.4 x squared over 2 plus just x minus, or I see a double negative, so it'll be plus e to the negative 0.3x over 0.3. I just saw this double negative right here, so I just thought of it as, I just wrote it positive. And again, we're evaluating this from 0 to 5. So fundamental theorem of calculus, fundamental, says first plug in your top number. So I'm going to do that first. So I have 2.4 times 5 squared over 2 plus 5 plus e to the negative 0.3 times 5 over 0.3. My goodness. Next, I will plug in my bottom number. So much happening. So now I'll plug in 0. Oh, I love you, 0. 2.4 times 0 squared over 2 plus 0 plus e to the negative 0.3 times 0 over 0.3. Okay, so I'm going to go ahead and enter this in the calculator. And hopefully we will have our answer. Let's see. 2.4 times 5 squared. And then this is over 2 plus 5 plus e raised to the power of negative 0.3 times 5 over 0.3 minus, I know the first term in the parentheses is 0, so is the second term. So I really have just e to the 0 over 0.3. So I'll just put minus e to the 0, which is 1 over the 0.3. And I get 32.41. Let's see if that works. Let's see. 32.41. Yay! All right, so try the homework for this. I'll probably do a couple more examples just as separate videos, like maybe number 8, because that's kind of strange looking, huh? And also like, uh, number 14, I like this one because it says, since Dr. Jones is a mathematician, she suggests building fences described by these functions, like these parabolas. Anyway, maybe I'll do a few like just separate videos to explain some of the other problems, but they all really follow the same idea. So you have the tools to do all of them. And you also have just like, that's the end of Calculus 1. So it's been a pleasure. Thank you for joining me this semester. Take care. Bye.